if A and B are two square matrices of order n, then another matrix B is said to be similar to A if there exists. This symbol means there exist. Okay, there exist. This we use in mathematics. There exists a non-singular matrix. There exists a non-singular matrix M such that this means such that. Okay, writing S and two dots here, so we write it as such that B is equal to M inverse A, then a matrix, a square matrix A is said to be diagonalizable. If it is similar to a diagonal matrix. That is, matrix A is said to be diagonalizable if there exists some matrix D. Okay, so that means if there exists some M such that there exists a matrix M such that M inverse A into M equal to D. Means if we can represent any matrix in this form. Okay, when square matrix A is said to be diagonalizable if it is similar to a diagonal matrix. Means after solving this one, we are getting a diagonal matrix. If you can find like that, then you can say the square matrix A is diagonalizable. Okay, so this is theoretical, but in practical case, we will not be using any of these things. We will be using some other method only. So, here D is the diagonal matrix, or we can say M diagonalizes this A. M diagonalizes this A and this is a diagonal matrix, or we can say it is the or M transform A to a diagonal matrix. Okay, so this is the definition. Now easy method to find out whether a matrix is diagonalizable or not. What we are going to do is, the first thing is that if all eigenvalues, this is the easiest way, if all eigenvalues are distinct, then the matrix is diagonalizable. Means when you are finding the eigenvalues, if all they are distinct, I think on that day I told you this one. If all they are distinct means different. You are getting three different values, suppose 1, 2, 3. Lambda equal to 1, 2, 3 you are getting. Like that means if you are getting different eigenvalues, then that matrix will be diagonalizable. Okay, without any other method, directly you can write it. Now, if the roots are if the eigenvalues are repeating, in that case, what we are going to do is, you will find two terms. That means we will be telling about algebraic multiplicity and geometric multiplicity. Okay, algebraic multiplicity means this case if the eigenvalues are repeating, or if the eigenvalues are not distinct. If eigenvalues are repeating, So eigen values are not distinct. Not distinct means they are repeating. In that case, what you will do, you will find algebraic multiplicity and geometric multiplicity. Okay. Now, what is algebraic multiplicity? Is the number of times an eigenvalue is repeated. An eigenvalue is repeated. That is the algebraic multiplicity. Okay. And there is another term called as geometric. Just wait. Geometric multiplicity is the number of eigenvectors associated with an eigenvalue. And if geometric multiplicity is equal to algebraic multiplicity, we may use AM, algebraic multiplicity, and geometric multiplicity we may use GM. Yeah, short geometric multiplicity, so GM. Now, if AM is equal to GM, means if algebraic multiplicity equal to geometric multiplicity for a particular eigenvalue, then we can say then the matrix is diagonalizable. This is what we are going to do. Okay. So now what does it say? Algebraic multiplicity means when you are finding out, suppose you are finding you have a characteristic equation, say lambda cube minus 11 lambda square plus 7 lambda. So like that you have a characteristic equation. Okay. After solving that, suppose you are getting lambda equal to 1, 2, 3. Then there is no question. Directly this matrix is diagonalizable. Okay, that corresponding matrix will be diagonalizable because the values are distinct. So when the values are distinct, we are going to get an eigenvector corresponding to each of these. Okay, then in that case the diagonal matrix means how you will get the diagonal matrix. Diagonal matrix D will be forming the diagonal matrix just by putting this eigenvalues as the diagonal elements and remaining all elements are 0. Obviously diagonal matrix means only diagonal elements will be there, remaining all will be 0. Okay, so if the values are distinct, then the matrix is diagonalizable and the diagonal matrix will be this one, and the transforming matrix means the M what we are doing. Okay, the matrix M inverse DM what you are doing here, this one. B equal to M inverse AM, yeah, D equal to M inverse A into, so here what we told, this one, B equal to M inverse A into M. So this is a transforming matrix. So after getting here, you will get 3 vectors and the transforming matrix M will be given by, but you will do corresponding to lambda equal to 1, you will have a vector. Now, like the previous method means last day we did. So using that method, you will find x1, then matrix you will get, suppose 1, 1, 1, then lambda equal to 2. Suppose you are getting say x2 equal to minus 1, 0, 1, and for lambda equal to 3, suppose you are getting x3 is equal to say 1, 0, 4. Okay, so corresponding to each eigenvalue, you are getting an eigenvector. Then what to do to get this M? What you have to do is just pick this and put it here. Take that vectors and write them as column vectors. 1, 1, 1, minus 1, 0, 1, this one, and 1, 0, 4. Then this will be the transforming matrix. Okay, so this is the easiest way to do. So if it is distinct, then diagonalizable. then diagonal matrix will be given by this one, that is just write the diagonal elements like this, and the transforming matrix M will be given by just arranging these vectors in columns. Okay, now if the values are repeating, that is the 0.2 and 3 is that one, that is suppose the values are repeating now. So in that case, suppose values, suppose 1, 1 or 2. Okay, eigenvalues we are getting as repeated values. Then also the diagonal matrix will be just this only, 1, 1 and 2. And this one you can write in any order also. Order in the sense, it is not necessary 1, 1, 2. You can write it as 2, 1, 1. Yeah, 1, 2, 1. 1, 2, here 2 and here 1, like that you can write. Okay, only thing is that the diagonal elements will be formed by this eigenvalues. Okay, so diagonal matrix. Now what is algebraic multiplicity and geometric multiplicity? So that is the number of algebraic multiplicity means number of times an eigenvalue is repeated. So here now lambda equal to 1. So for lambda equal to 1, it's algebraic multiplicity. For lambda equal to 1, algebraic multiplicity means how many times this 1 is repeating. So 1 is repeated 2 times. So algebraic multiplicity is 2. That is the second point. Algebraic multiplicity is the number of times an eigenvalue is repeated. Okay, so how many times it is repeated, that is what, that is the algebraic multiplicity. How many times an eigenvalue is repeated, that is algebraic multiplicity. Now geometry, so here for lambda equal to 1, AM is 2, and for lambda equal to 2, algebraic multiplicity is 1 because it is only one time. Okay, now geometric multiplicity means number of eigenvectors associated with an eigenvalue. Now suppose when lambda equal to 1, suppose I got two vectors x1 and x2. We know how to do this one, x1 and x2, I got two vectors. Okay. Then geometric multiplicity also will be 2. So geometric multiplicity is number of eigenvectors associated with a particular eigenvalue. So lambda equal to 1, I got two vectors. So geometric multiplicity is 2. Now same way for lambda equal to 2. For lambda equal to 2, I am getting another vector, say x3 equal to 1 vector I got. So for lambda equal to 2, algebraic multiplicity is 1 and geometric multiplicity also 1. If it comes like this, then the matrix is diagonalizable. That is what is written here. Okay, geometric multiplicity is the number of eigenvectors associated with an eigenvalue. So if it comes like this, means it is not like say AM for lambda equal to 1, algebraic multiplicity 2 and geometric multiplicity also 2. Suppose for lambda equal to 2, algebraic multiplicity is 1, and this case will not come like this. For example, I am just telling. So algebraic multiplicity is 1 and geometric multiplicity is suppose 2. Suppose you got two vectors for that. Okay, in this case the matrix will not be diagonalizable. It should be both. So means what many eigenvalues are there, that many times you have to find AM and GM, and it should be same in all the cases. Okay, so here also it should be 1, then it is diagonalizable. Now what will happen? Suppose for lambda equal to 1, I got only one eigenvector. For lambda equal to 1, we got only one eigenvector, so it is 1. Geometric multiplicity is 1, and for this say algebra AM is also 1, GM is also 1. Then also this is not diagonalizable because here AM is 2 and GM is 1. Okay, so if AM equal to GM for a particular eigenvalue, then the matrix is diagonalizable. So for particular eigenvalue means you have to take all the cases. But many eigenvalues are there, that many times you have to do AM, GM, AM, GM, AM, GM, like that. Okay, so if in all the cases if they are same, then it is diagonalizable.